Hey everybody, welcome back. Now that you're familiar with what a set is and what subsets are, we can start looking at operations on sets. That is to say, the way that we can combine and separate and distinguish and create new sets. So let's jump right in. Okay, so the first way that we can build new sets is by taking the union of the sets. And we represent union with a symbol that looks like the letter U, but it's technically not, but close enough. And A union B consists of all the elements that are in A or B. In other words, we form a union of all of their elements. So if A consists of 1, 2, 3, 4, and 5, and B consists of 1, 3, 5, 7, and 9, then A union B has to consist of all of those elements combined. So we have 1, 2, 3, 4, and 5 from set A. Now we don't want to list 1, 3, and 5 again, we've already listed them, but we do want to list 7 and 9 since they're part of our union, and that is the union of A and B. Notice that the union has 7 elements, whereas A and B each had 5. It's pretty normal for the union to be bigger, that is to say, to contain more elements than either of the sets that are used to build the union, though that's not always true, and we'll see that a little later. What about our second example here? C consists of 1, 3, 5, 7, and then the 3 dots or the ellipses mean, and so on, so that goes on forever. We could call these the odd numbers. And D consists of 2, 4, 6, 8, going on forever. Those are the even numbers. Then what will C union D consist of? That is to say, what do we get if we combine or form a union of all the odds and all the evens? Well, 1 would be in that set, 2 will be in that set, 3 will be in that set, 4 will be in that set, 5, and it doesn't take too long to figure out that all odds and evens are going to be in this set. That is to say, this forms the set of integers, and we'll use 3 dots to show that that goes on forever, so we don't have to write them all. And there's the union of C and D. C and D and the union of C and D are called infinite sets. That is to say, it's impossible to list all the elements, so we just establish the pattern and leave it at that. A and B on your screen are finite sets. That is to say, they only contain 5 elements each. We can list all those elements. Okay, here's a practice problem for you. We're going to use set builder notation as presented in our previous lesson on sets and subsets. If this doesn't look familiar, you might want to go back and rewatch the sets and subsets lesson. But E consists of all elements X such that X is a state name beginning with the letter W. F is the set of all elements X such that X is a state name that ends in N. So what would E union F look like? Pause the video and unpause when you're ready to see if you have that set listed correctly. Okay, well, if we name the specific elements of E, states that begin with W, they are Washington, West Virginia, Wyoming, and don't forget Wisconsin. F is the set of all names that end in N, so that's going to consist of Washington, Oregon, Michigan, and Wisconsin. So E union F, we're going to pool all of these together, but we don't need to repeat any, and so we're going to have 6 elements, all of the W states and the 2 other states that end in N, Oregon and Michigan. We don't need to list Washington or Wisconsin twice. Okay, the second way that we can combine sets is by building their intersection. The intersection of 2 sets, A and B, and we represent the intersection with what looks like an upside down U. I sometimes think of that as being kind of like the letter A for and, because elements in the intersection have to be in A and B. But the intersection consists of all elements that are in both set A and set B. That's typically going to be a smaller set. We don't want any elements that are in either. We want elements that are in both. So if once again A is 1, 2, 3, 4, and 5, and B is the set 1, 3, 5, 7, and 9, then A intersect B will be the overlap, or the elements that are in both. And the elements that are in both here consist of the numbers 1, 3, and 5. And that's our intersection. Notice here that the intersection is smaller than either of the sets used to build the intersection. And that's pretty common, but not always true. For our second example here, C still consists of our odd numbers and D consists of the even numbers. So what will C intersect D look like? What are the elements that are in both? Well, are there any numbers that are both odd and even? That is to say, what numbers are in 1, 3, 5, 7, and so on, and 2, 4, 6, 8, the evens? There are none. And so we have a set that's empty here. There are no elements in this intersection. These two sets don't intersect at all. There's two ways to represent that. One way is to put our braces to show that we have a set but don't put anything in it at all. That's the empty set. Or another way to express the empty set is a circle with a line through it like that. Both of those things represent that we have a set that contains no elements, and that is the empty set. So I would like you to build a little bit more on the practice we did earlier. E is the set of all states that begin with W. F is the set of all states whose name ends in N. What would the intersection of E and F be? Take a minute, pause the video, think about that, and unpause when you're ready to see the intersection. Okay, well, we saw that the union were all the W states and the states that end in N pooled together. We joined the two sets. The intersection will consist of states that both start with W and end in the letter N. And of course, there are only two of them. And they are, of course, Washington and Wisconsin. Start with W and end in N. That's a pretty exclusive club. All right, well, in addition to intersections and unions, the third operation we can apply to sets is the complement. The complement of a set, and we represent that by putting a little line over the name of the set, consists of all the elements in the universe, that is to say, of all possible element entries that are not part of our set A. So for example, let's let A be the set of days of the week, Monday, Tuesday, Wednesday, Thursday, Friday. Okay, well, let's first of all determine what our universe is. And of course, the universe then will be Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. So if A consists of Monday, Tuesday, Wednesday, Thursday, and Friday, or in other words, the weekdays, then the complement of A must be the days that are not in A, and that would be our weekend days, Saturday and Sunday, and we have our complement. Okay, let's look at another example. Let's suppose that the universe of elements are all values x such that x is a hexadecimal digit. That's going to be the numbers 0 through 9 and a through f. Okay, so we wouldn't have to list all the elements in the universe, but I'm going to do that. The set E consists of all of the even digits that are inside of our universe. So we always consider 0 to be an even number. So the even numbers will consist of 0, 2, of course, 4, 6, 8, and A, C, and E since they represent 10, 12, and 14. And there's our even digits. F consists of all of the decimal digits. So those are, of course, 0 through 9. And now we can determine the two complement sets that are given. The complement of E then will consist of all of the elements that are not in E. In other words, all the elements that aren't even, well, those would be the ones that are odd, including, of course, 1, 3, 5, 7, and 9, but also B, D, and F, since those are 11, 13, and 15. And what will be in the complement of F? Well, the complement of F will consist of all the elements that are not in F. F contains all the numbers that are hexadecimal that are within our universe, but also decimal digits. So the complement of F will be everything that's in the universe, but not in F. And that, of course, is going to be our digits for 10 through 15. A, B, C, D, E, and F. And there's our complement. So let's wrap up our work with this topic by looking at a few examples of combined operators. For the purposes of these examples, let's let our universe be all the decimal digits 0 through 9. We're going to let A consist of the binary digits 0 and 1. B will consist of all values of x such that x is odd. And C will consist of the subset of the universe 6, 7, 8, and 9. And let's find all 6 of the sets defined here. So our first one, that would be the complement of A union C. Well, before we can find the complement of A union C, we should probably find out what A union C is. A union C will consist of all elements that are in A and C combined. So that will consist of 0, 1, 6, 7, 8, and 9. Then the complement of A union C will be all the elements in our universe that are not in A union C. And so 0 is in A union C, so is 1. 2 is not, 3 is not, 4 is not, and 5 is not. 6, 7, 8, and 9 are. So the complement of A union C will consist of 2, 3, 4, and 5. Let's take a look at our next one. The complement of B intersect C, well, we can't figure out what that is until we know what B intersect C is. So let's start by finding B intersect C. Well, that's going to be the set of elements that are in both B and C. So B is all the odd numbers. C consists of 6, 7, 8, and 9. So what are the odd numbers that are also in C? Well, that would consist of just 7 and 9. Those are the only two numbers that are in B and C. So if we want the complement of B intersect C, then we want all the numbers in our universe that are not in B intersect C. So all the decimal digits that are not 7 or 9, that's going to consist of 0, 1, 2, 3, 4, 5, 6, not 7, 8, and not 9. And so that is the end of our set. That is the complement of B intersect C. Notice that our universe has 10 digits in it. And so since B intersect C has 2, the complement has to have the other 8. Okay, so now we have the complement of B union C. Now you can see that the language here gets a little bit ambiguous. When we say the complement of B union C, that could mean that we're going to take the complement of B union C like we are here, or we could be asking to find B union C and then take the complement of that. That's why the notation has to be a little bit more explicit, because the language is ambiguous. But we have this well defined, we can figure out what this is. Before we can find out what the complement of B union C is, we better figure out what the complement of B is. So let's start out by listing the complement of B. Now B are all the digits that are odd, and therefore the complement of B will be those that are even. 0, 2, 4, 6, and 8. Now C is given there on your screen, 6, 7, 8, and 9, and therefore the complement of B, right here, union C, shown on your screen, if we pool all those together, we're going to have 0 from the complement of B, 2 and 4 from the complement of B, 6 still from the complement of B, 7 which comes from C, 8 which comes from both, and 9 which comes from C. And there are the elements of the complement of B joined with those from set C. And here again our notation told us that we had to start by finding the complement of B before we can combine it with the elements of C. Our next one, A union B intersect C. Here we need to set a parentheses to show exactly what operator we need to apply first. And so the first thing we need to do is we need to find A union B. So we can do that pretty easily. A union B is going to consist of all the binary digit 0 and 1 combined with the odd digits from set B. And that'll consist of 0, 1, 3, 5, 7, and 9. 0 and 1 from A, and 1, 3, 5, 7, 9 from B. Now we're going to take those elements and find the intersection with set C. Since C consists of 6, 7, and 8, and 9, what elements are going to be in A union B and in C? Well, 0, 1, 3, and 5 are not in C, so they're not in the intersection. 7 is in C, and 9 is in C, and so the only two that are in both are 7 and 9. And there's the intersection of A union B and set C. Our next one, A intersect C union B. Well, we better start by finding out what A intersect C is. Our parentheses, just like in normal arithmetic, tell us to give an operator top priority, or that it should be done first. So A intersect C, what are the elements that are in A and C? Well, as it turns out, A consists of 0 and 1, C consists of 6, 7, 8, and 9. A intersect C is the empty set. There are no elements in there. But B, since B consists of all the odd digits 1, 3, 5, 7, and 9, we want to find the union of A intersect C, which is empty, and B, which is not. And if we join the empty set with the odds, we end up with the odds. These are the only numbers that make it into the union. There are no numbers in the empty set. So our union will consist of 1, 3, 5, 7, and 9. That's kind of a tricky one. And our last one, we want the complement of C intersected with C. Well, let's list these. C is shown on your screen, that's 6, 7, 8, and 9, and therefore the complement of C is going to be 0, 1, 2, 3, 4, and 5. Since C is 6, 7, 8, and 9, we can find their intersection. The intersection of C and its complement, so we're looking for the numbers that are in both the complement of C and C. And of course, there are no numbers in the set and its complement. And in fact, it's one of the properties of sets that if you intersect any set with its complement, you won't find any common elements. That gives us the empty set, or if you prefer, a circle with a line through it. Okay, so why don't you try a few for practice here. I've given you a universe of the digits 0 through 6 and 3 sets, P, Q, and R. See if you can determine what sets are defined by each of the 6 combined operators shown on your screen. Work all those out and unpause to see the solution to each. Okay, our first one, we want the complement of P intersect Q. So before we can find the complement of P intersect Q, we better figure out what P intersect Q is. So let's start with that. Since P consists of the numbers 1, 2, and 3, and Q is all the even numbers, then P intersect Q will be the numbers that are in both, where P and Q intersect. And so the number has to be even and in set P, and the only number that's in both is the number 2. Since P intersect Q is the number 2, then we can find the complement of P intersect Q, and that'll be all the numbers in our universe of 0 through 6 that are not in P intersect Q. So that'll consist of 0, 1, not 2, 3, 4, 5, and 6, and there we are. There was 7 elements in our universe, 0 through 6. There's 1 element in P intersect Q, and there's 6 elements in the complement of P intersect Q. Our next one, the complement of P union R. Well, let's start by figuring out who the elements in P union R are. So P union R will consist of all the elements that are in either P or R. So the elements in P are 1, 2, and 3, and the elements in R are 5 and 6. And so P union R will consist of 1, 2, 3, 5, and 6. But of course, we want the complement of P union R. So that'll be all the numbers in our universe that are outside of P union R. And so that'll consist of 0 and 4. And there's our set. Okay, our next one, the complement of R intersect R. Well, R consists of the numbers 5 and 6, and the complement of R is going to be made up of all the numbers that are not in R, 0, 1, 2, 3, and 4. But it really doesn't matter because the intersection of R and its complement, that is to say the numbers that are in the intersection of R and the numbers not in R, of course there aren't going to be any. We didn't actually need to even know what the sets R and its complement are. Anytime we intersect a set with its complement, we're going to be left with the empty set because there's no way that a number can be in both a set and its complement. If a number is in the set, it can't be in the complement. We're done. Our fourth one, P intersect Q, union Q intersect R. Let's start by finding P intersect Q. So we want all the elements that are in both P and Q. Well, we actually saw this one earlier. P intersect Q, that was part of our first set that we solved. And so P intersect Q was the only even number that's also in P, and that consisted of 2. Now let's find out what Q intersect R consists of. Q intersect R will be all the elements of Q, which are the evens, intersected with R, which is 5 and 6. The only number that's in the intersection or in both will consist of 6. So P intersect Q consists of 2, Q intersect R consists of 6. Then we can conclude that 2, P intersect Q, union 6, Q intersect R, is going to consist of the set containing just 2 and 6. And that's all we can do there. Okay, our fifth one, the complement of P union the complement of R intersect Q. Let's figure out what our complements are here. The complement of P will be everything that's not in P. P consists of 1, 2, and 3, so the numbers that are in our universe but not in P are 0, 4, 5, and 6. The numbers not in R will be everything in the universe except 5 and 6, so it'll be 0, 1, 2, 3, and 4. That gives us all the information that we need to solve for what elements are in this set. Complement of P union complement of R, we're doing this part right here. And so we join the complement of P with the complement of R, and we end up with 0, which is in both, 1, which is in the complement of R, 2, 3, 4, all from the complement of R, 5, and 6, which are in the complement of P. So not in P union, not in R, we end up with our entire universe. Now we want to find out where that intersects with Q. So what numbers are both in this set and in Q? Well, Q consists of the even numbers, and this turns out to be our entire universe. So the numbers that are in both will be just the even numbers, 0, 2, 4, and 6. And in fact, you might notice that if we have an intersection with any set and the entire universe, then the result will be just that smaller set. But we'll see that in one of our properties a little bit later. And our last one, let's find the complement of Q union Q. Well, of course, we already know from what's given on our screen that Q consists of the even elements, 0, 2, 4, and 6. And then we also know that the complement of Q will consist of the odds, 1, 3, and 5. Now, if we want the union of these two sets, we're going to put them together. And if we put them together, we end up with all the evens and the odds, 0, 1, 2, 3, 4, 5, and 6. And that is, of course, the entire universe. And just as the intersection of a set and its complement yields the empty set, the union of any set and its complement will always yield the entire universe. And again, we're going to see that in one of our properties in a future lesson. Okay, so that wraps up this lesson, but of course, I just want to review those three operations on sets with you that we'll be using going forward and using to build a logic system in just a few more lessons here. First of all, the union of two sets consists of all the elements that are in one set or the other. We combine those two sets usually into a bigger set. But the intersection of sets is the set of elements that belong to both of the other sets at the same time, and usually that forms a smaller set than either of the two that you started with. And finally, we can take the complement of a set by collecting all the elements in the entire universe that are not within the set itself. And that, of course, can be bigger or smaller depending on how big your initial set was. Okay, so you're going to have some homework problems similar to the ones we did in this lesson. Make sure you work through those. These concepts are important for the logic systems we're going to be building later, so make sure to get help if any of these things are not clear. Otherwise, we'll see you in the next lesson.